Okay, welcome everybody. Good morning, good afternoon, wherever you are. Welcome to another AmeriFlux Year of Remote Sensing webinar. It's great to see you. We have two speakers today, Dr. Martin Beland and Dr. Shi Yang. And we're gonna hear two short talks from each of them, and then we have some time for Q&A. So let me introduce our first speaker, Martin Beland. He's an associate professor at Laval University in Canada and is an expert in LiDAR, biophysical modeling, spectral measurements to investigate function and structure of forest ecosystems. Please take it away.
Thank you. So I'm going to share my screen. You guys can see this?
Perfect.
Yeah. Okay, so thanks for the invitation. I'm going to, in my part of the talk, so I'm going to talk a bit more about the different LiDAR systems that are available and how they've been used at Flux sites and how we are using it in my lab, which is the Digital Forest Lab, to study the mapping of leaf area and radiative transfer in forests at Flux sites. So I'm going to start with describing a bit what LiDAR is, the different system types, and I'm going to talk a bit about recent usage of LiDAR at the Flux sites, and you're going to see that it's mostly UAV-based LiDAR, which is becoming very popular. So I'm going to show a couple of examples of how they were used. I'm going to introduce a new network that's called StrikeNet and how it can be interesting for people of AmeriFlux. And then I'm going to finish with how we are using in my lab terrestrial LiDAR to map 3D structure. So I think many people know about LiDAR. I'm going to quickly introduce the technology just to make sure everybody understands that it's just a system that emits laser pulses, and it's usually in a scanning pattern. And the return energy is measured with the time of flight recorded most of the time. And from there, we determine the exact location of a hit between a pulse and a target. Sometimes the intensity of the light is also measured, and we can derive some useful information from there. The technology is becoming more and more common. A lot of people know about it. It's in the phones, many phones now, it's in cars. So the cost of the technology is also decreasing in most cases. So in forest, it holds a lot of potential for improving how we measure canopy structure. Different system types. I'm showing here airborne LiDAR, which I think most people know, UAV based LiDAR. I have on the right, I can't see it on my screen because there's some people showing there, but on the right top, I have the spaceborne LiDAR, for example, JEDI, then the TLS, which is terrestrial. The SLAM is associated with a mobile LiDAR. It's less used in general at Flux sites. And then we got the personal canopy LiDAR, which is been used at some cases, but has limited usage. So I'm going to focus on the three systems that are below here when I'm talking about the different systems. So airborne, UAV, and terrestrial. So they differ mostly in the resolution, and here by resolution we mean mostly the size of the pulse. So when it's hitting a target, the different systems are going to have different size of pulse. So in airborne, it's typically around 10 centimeters. So that determines kind of the level of detail that you're able to get from there. So UAV is significantly higher. I see here, I show for 5 centimeters. Sometimes it can go lower. So you get more detail from a UAV. Then from an airborne is very good at covering large areas with a manned aircraft. UAV is smaller areas, but this area coverage is more in line with typical footprint from a flux tower. So the UAV I'm going to suggest here is in terms of coverage and resolution is a good match with the size of the footprint from a flux tower. The terrestrial LiDAR has a much higher resolution, but the coverage is much smaller. So it is smaller than the typical footprint of a flux tower. So main advantage and disadvantage, airborne has been used quite a bit in the past at flux sites. So it's very good at covering large areas in a more heterogeneous manner. It is costly. Logistically, it's more complex because you need an airport close by. It's a manned aircraft. Sometimes you got people on the ground. So logistically, it's heavier compared to UAV LiDAR, which is much simpler. You don't need an airport. You have a lot more detail, so a higher resolution. It's easier to make repeated measurements through time if you want to do that. And sometimes people have been quite often putting a hyperspectral sensor on the UAV as well. So you can couple those data, which is interesting. The disadvantage of the UAV, though, is the processing method. So as we go down from airborne towards terrestrial LiDAR, the complexity of the processing tools tends to increase. So the expertise level you need to process the data is higher. And as you go to terrestrial LiDAR, the level of detail is much higher. You get more information about your within canopy structure. You're able to separate what's wood from leaf material using the intensity of the signal, which is a big advantage. Disadvantage on this side, of course, the plot size is small, relatively small compared to the footprint of the tower, and the data processing is significantly more challenging. So typical products we get from LiDAR at flux sites, we get, of course, things that people are used to: canopy height, crown dimensions. We can get gap fraction, leaf area, biomass, stem density, foliage clumping, gap size, and connectivity, sometimes also for habitat studies and aerodynamic parameters. And the message I want to send here is that some LiDAR systems are better adapted to derive some of those informations than others. And it's nice to have some, let's say, advice from somebody who's used these systems before to figure out which one is the best to use. So when we're using typically LiDAR systems at flux sites, I think there's a few, mainly here I separate in 4 different categories of things we need to determine. So which platform you're using, is it airborne, UAV, or terrestrial? Who's going to carry out the survey? Sometimes you do need some expertise to do this. So it can be a collaborator or a private company in some cases. The protocols that are going to be used to acquire the data, sometimes you need to set the instrument in specific places if it's terrestrial, or determine the height of your flight if it's airborne. The instrument also has some different settings you can use. And lastly, and very importantly, which tools you're going to use to process your data. And personally, I've seen many instances where people either acquired LiDAR data or even purchased instruments sometimes. And once the time comes to process the data, they realize that it's more complicated than they were expecting. And this is slowing down their progress. So make sure you have an idea of how you're going to process this data. So I'm going to show now, as I said, I think personally UAV is very well adapted. It's becoming more popular for use at flux sites. So I'm going to show a couple of examples. I did a quick research in the literature to see how LiDAR has been used in the recent years. I think I started from 2019. I found a couple examples that were kind of interesting. One is the estimation of the roughness length in different directions. So different wind directions, the people, they wanted to know how that was affecting the roughness length. So they have an heterogeneous footprint, and they were curious about how wind was behaving with the surfaces in the footprint. And so this is based mainly on the height of the objects and the difference in height and different directions of incoming wind. So they use the UAV for doing this, which has a very obviously a very high resolution and very high accuracy as well. The second example is from a site where there was multiple flux stations installed in areas that had different forest treatments that was brought to the site. So they use the UAV to fly each of these sites individually and derive metrics related to structural complexity, and they wanted to relate those to GPP at the different sites. And this is an interesting application. The UAV is easy to launch at each of these areas, and it provided, as you can see on the right, high level of detail on the forest structure. And the goal of this was to look at the how to better simulate the response to different management practices. So this is another interesting use of the UAV LiDAR. So now I'm going to talk about a different type of instrument that I haven't talked about yet. It's behind the launch of a new group that's called StrikeNet, and the goal is to monitor forest structure in the long term. So I brought here a recent perspective paper that was highlighting that long-term records of, in this example here, partial defoliation was often lacking at FluxNet sites. And the authors were saying that there's no yet standardized ground-based measure of the structure at across sites, and this is limiting the comparison across the sites in the network. So, and this is where I think StrikeNet, what the group is proposing to do, might be of interest to AmeriFlux. So this new instrument is autonomous, so it's meant to be left in the field, actually. It's weatherproof. All the sites so far in StrikeNet are using that same instrument. We had a workshop last May to discuss how we're going to develop this initiative. So the goal is to monitor structure through continuous LiDAR measurement. And continuous, we mean you can scan once a day, you can scan twice a day, every day. And the information you're deriving from there is leaf area index or leaf area density vertical profile. And here I mentioned leaf area density, but later on we're going to see it's actually plant area density so far, because we're not differentiating the leaves from the wood in this data so far. So it's a standardized way of acquiring the LiDAR data and processing it. The group is suggesting to process everybody's data using the same processing chain. So you would just put that instrument in the field, send it to StrikeNet, and then you return the product. So the instrument looks like this here. So it's meant to be operating in wet, hot, cold conditions. This is what it's built for. I'm not going to go through all the technical details of it. This is built in Australia, this instrument. So this is the example of products we can derive from this. So at the top is the plant area index total, and at the bottom right is the plant area vertical density profile. So you can see through time how the overstory and the understory are evolving, which can be interesting if you're looking at even phenology, different phenology in the overstory and understory, or if you had a disturbance in your canopy, so how it's responding to that disturbance. So far, the sites that are using the instruments are in Australia mainly operationally. This StrikeNet is a European led initiative, so many sites are planned in Europe, and there is one site at the moment in the US. So some little practicalities with this one. It has communication capacity, so it can transfer the data automatically to the tower, and it is operating from solar power. The cost is about $19,000 USD, as I understand. So if you're interested in this instrument or the network and you want some advice or information, you're welcome to contact me by email. So now I'm going to switch to terrestrial LiDAR, which is the system that we use mostly in my lab. So terrestrial LiDAR, most of you know, this is very highly detailed data. We can see the leaves and the wood. We can see the wood structure in much detail, the leaf area. And the reason why we use it in the lab is the main reason is to characterize structure in a way that would allow us to better understand and model radiative transfer in forest. So we're moving away from more simplistic representation of the canopy structure to a more detailed representation. And we do this mainly to investigate foliage clumping at different scales, spatial scales in the canopy. We want to model the interception of radiation by the leaves and the wood in the canopy, and we want to understand the drivers of canopy reflectance. And we do this by using voxels. So these are cubes, and in each cube within an array, our plots typically they're about 60 meters by 60 meters. And within each of these cubes, we look at how many laser pulses come in and how many laser pulses are intercepted by wood or by leaf material. And using Bayes' law or contact frequency methods, we then derive a density of foliage inside each of these cubes. And we have these cubes for the whole array or the whole plot. And so we know where the leaf material and the wood material is located. So far, we've surveyed 7 sites that have flux towers. So each of these sites are, they have a plot of this size inside the flux tower footprint. Most of them are in the US, and one of them is in tropical forest in Malaysia. And next summer is also planned to do more work in the temperate forest. So within each of these cubes here, we initially assumed that leaves were randomly distributed in there, but it was that assumption was challenged at some point, and we started looking at whether this was the case or not. And it turns out that when we collected, so here branches at different heights in the canopy and in different environments, in temperate forest and in savannas. So it turns out that leaves around branches in savannas, they are pretty much randomly distributed. So we can assume this behavior when we're using Bayes' law to derive leaf area density. But in temperate forests, at the top of canopies, the leaves are very clumped. So the leaves, they're very bunched around around the branches, very high density. So they're shadowing each other. So they're very highly clumped. And with the terrestrial LiDAR, we're able to estimate that level of clumping. So the way we do this is we take a branch from a different heights in the canopy. We fix it on a tripod in the same way it was like oriented when it was in the tree. And we measure the transmission of laser light through that branch or that box. And after we make the LiDAR measurements, we collect all the leaves inside the box and measure the leaf area of those leaves. And we also, from the LiDAR data, collect the orientation of each of these leaves in space to get an estimate of the projection factor associated with the orientation of the leaves. And when we do this, then we can isolate omega, which is the clumping factor. And what we found is, at least this is in a maple, sugar maple in a temperate forest, the canopy, so the branches at the top of the canopy are very highly clumped. And as the LAI, the cumulative LAI increases as we go down further in the canopy, they are more separated from one another. And they are then, we come, this graph I'm showing here is integrating actually the small scale clumping, so the shoot scale, and the larger scale clumping at the plot level. So when we go down further in the canopy, the clumping factor integrating all these scales is about 0.8. But higher up in the canopy, it is highly clumped. So this is a behavior that was it was suspected, I would say, but this is the first time that we're actually able to measure it. Once we know the distribution of the material in the forest and we know how aggregated it is, we can put these voxel arrays into radiative transfer models using ray tracing approach. And we can measure the radiative transfer. In this case, I'm showing here near infrared, the interception of near infrared in two contrasting structures, so at Harvard Forest and at the Smithsonian. And we can differentiate the interception of light by the wood and the leaves, which is very interesting for a number of reasons. We can also simulate the radiation that's being reflected off the canopy. And in this case, we model the reflectance and compare it to an actual observation. So this on the left is an observation from the NEON Airborne Observatory of the same area, of the same plot at the Smithsonian in Maryland. And what we can see is that there are some differences between modeled and observed reflectances, but there are some similarities as well. And this is, giving us some confidence that slowly we're getting better at doing this kind of thing, and we can start learning some things about the drivers of this reflectance. So separate what is coming from spectral properties and what might be coming from structural properties. So this is conclusion of my part of the talk. So in conclusion, I think LiDAR technology, it just keeps evolving. Of course, UAV LiDAR is increasingly becoming popular. It's well adapted to the scale at which we typically work for flux tower sites. So I highly recommend working with this technology. Data processing remains a challenge for the most LiDAR data. So collaboration with people that have experience is a very good thing, I think, still. And when you're looking at using LiDAR data at your sites for different projects, I encourage people to seek out advice with people that have used these systems. So with that, I'm going to pass it on to Xi Yang, who's going to talk more about terrestrial LiDAR. Thank you very much.
Thanks a lot, Martin. Our second talk comes from Dr. Xi Yang, who's an associate professor at the University of Virginia. And he's an expert in climatic controls on vegetation photosynthesis and related plant functioning, the feedbacks of vegetation to the climate, and the impact of climate change on vegetation phenology. Yeah, please take it away. Thanks.
Thank you, Christine. And thank you, Martin, for that excellent introduction. I think that sets the stage to some of those TLS scanning applications that I'm going to talk about in this presentation. And I also want to start with acknowledging my co-authors who are listed on the lower part of the slide, and my sponsors. So I'm going to talk about terrestrial laser scanning sheds new light on ecosystem structure and function, no pun intended. But anyway, so our starting point is when we look at the ecosystem processes, they're controlled at various spatial scales, like, for example, photosynthesis, transpiration, light absorption, the changing temperature, stomata conductance, all of those processes happen at the leaf scale. They're controlled a lot at the leaf scale, but also they're controlled by process at the canopy scale, like the arrangement of leaves on the canopy, the sunlit and shaded tree fractions, where you are as a leaf in the canopy also matter a lot in controlling all those processes. And this is year of remote sensing for AmeriFlux. And one of the questions that people oftentimes ask is, well, when you make a remote sensing measurement at a flux tower, what drives that change in this optical remote sensing signals? Let me move my mouse this way. And take solar-induced fluorescence as an example. Solar-induced fluorescence, some of you don't know, is the light emitted by plant during photosynthetic processes. And if we write an equation to describe SIF, is basically a product of how much light coming in, that's par, multiplied by the fraction of that par gets absorbed by the by chlorophyll, that's a FA par there, and then multiplied by the probability of that absorbed radiation gets emitted at fluorescence, which is CF here, and multiplied by this FESC, which is escape probability, which is basically how much of that emitted fluorescence eventually emit the canopy and get captured by the sensor. We can even further decompose this into this equation here, where you describe FA par as a product of canopy interceptance with, this is INR there, multiplied by 1 minus this single scattering albedo. That gives you the mean average leaf absorbance of the canopy, and then multiply by those two terms there. And you can see some of those terms in this equation, like canopy interceptance, escape probability, they're controlled by canopy structure, whereas some other process like FEF is more likely controlled at the leaf level, through photochemistry. So the main take-home message is in this next slide is to understand what we measure at the canopy scale, which is on this right-hand side of this figure, where we measure fluorescence, reflectance, all the remote sensing signals at the canopy scale. To interpret those, and to go down to the step 1 here at the photosystem scale, you really need to characterize canopy structure. Characterizing canopy structure will help you to decompose the signal into the structural control of the signal and more like a photochemical control of those signals. So you might want to ask this question: what do you mean by vegetation structure, right? So take a look at this beautiful tree scanned by our UVA undergrad Maggie Cox recently on campus. Vegetation structure to us is kind of like a multifaceted concept. From the tree's perspective, it include traits like tree height, crown size, etc. But I want to quote this paragraph from the book by Monsoon and Baldacci, that leaves do not carry out their physiological functions as isolated units. Rather, they interact with the tens of hundreds of other leaves that surround them in a canopy, and much of that interaction is determined by the architectural placements of leaves on branches and in turn branches on stems. So to us, there are a few metrics of vegetation structures that are important. For example, leaf area index, and many of us know that it's important. And also leaf angle distribution and the clumping that Martin just mentioned. I'm going to focus on leaf angle distribution because it's a very important metric, but it's hard to measure. We know it's control light, interception, absorbance, and other canopy fluxes and optical signals. But like for tall trees like this, measuring its leaf angle was a challenging task. So let's go back in time and look at how people study leaf angle. I'll give you a few examples. This example is from Darwin. He wrote a book in 1880, The Power of Movement of Plants. He actually documented the leaf movement of over 200 species. And most of them, if not all, mostly, as you can see from this figure, seedlings or plants that are small. So, but he basically tracks the change of leaf angle of individual leaves throughout the period, sometimes over an entire week. And you can see this change of leaf angle up here on the upper right-hand corner. But no, he did not record any changes in tree leaf angles and over trees. And I actually, another example here I want to mention is the Fung example. This is about an ancient Chinese poem, Light Rain in the Early Spring by Han Yu from the Tang Dynasty. And this is also an example that are oftentimes used by the late Xiao Li to talk about the impact of bidirectional reflectance distribution function. But is this also a great example of the impact of leaf angle? So in the poem, there's a line saying, though one sees the color of grass from afar, if one gets closer, it's not really there. This is basically a demonstration of the vertical leaf angles of grasses. You see them from, you clearly see the green leaves from the side, but as you get closer, because of the vertical leaf angles, you see more soil background, so the grass field look less green. And there's also an American way of saying this, which is the grass is greener on the other side. So there are some early characterization of leaf arrangements in canopy, like more recently. This is from Halley, Oldman, and Tomlinson from 1979. And they actually documented over 20 to 30 tree structural models like this, showing in this slide. Mostly those are tropical plants. And you can also see they have models for trees that grow at different growth stages. It's a rare effort at the time, really dedicate, drawing here, but also you can see that the description of leaf arrangement on those models are rare, like not very good. So let's get back to leaf angle here. So just to make sure everyone is on the same page, leaf angle in this presentation, mostly I'm referring to leaf azimuth angle, which is theta L here, right here. It's basically the angle between the leaf surface and the horizontal plane, or the angle between the leaf normal and the zenith. You can take it that way. Also, there's a leaf azimuth angle, theta S here. And if you take the statistical distribution of leaf inclination angle from a whole canopy together, it's a leaf angle distribution as shown here from this figure. X-axis is the leaf inclination angle. More vertical leaves are on the, have on the right-hand side of this figure, larger values. Horizontal leaves are more on the left-hand side. And there are multiple types of leaf angle distribution that modelers often use. For example, erectile phi, which is this gray line here, shows that most of the leaves on the tree canopy are like vertical, as the name suggests. You also have planophile leaves down here, which is this dashed yellow line, and that shows this most of the leaves are more sort of a horizontal in some way, and there's this purple dots here. That's more like a spherical distribution. Imagine you have a perfect sphere. You tape leaves, all the leaves on the canopy all together on this, cover the entire sphere. The statistical distribution of the leaf angle of that sphere is spherical. So basically, those are major types of leaf angle distribution. But oftentimes people just stick with those 6 types, whereas in reality, in nature, leaf angle is quite variable. I'm going to show a few examples. This is from my friend Guofeng Miao, and actually I think Guofeng is also in the audience. She measured change of leaf angle of a soybean field. Look at the timestamp there. It just happened like within a few hours in the morning. This is in central Illinois. It looks like the plants just woke up and started to stretch, but you can see the change in leaf angle is quite dramatic in this video here. Well, it's this dynamic leaf angle changes is not limited to soybean. There's one earlier work by John Gammon and Rob Piercy. This, I believe, is in California, some shrub species, where he noticed that there is a significant diurnal changes in leaf angle for those plants. And you can see some of those changes could be as large as, let's say here, this is about 40 to 50 degrees. Depending on which side of the canopy you are. There are also significant interspecific variations in leaf angle. This is from Yan Pisek work in, this is in 2022. He basically can see that there are some temporary deciduous forests in Europe, and the variation in mean leaf inclination angle could be as large as 50 degrees, something like that. And also for the same species, there are also intraspecific variations in leaf angle. This is our Rhabdopsis thiniana that are taken from different places and grow in the common garden. And you can also see where they come from. So x-axis is latitude. Where they come from also determines, sort of correlate with the mean leaf angle of that plant that grow in the common garden. So if you're from a lower latitude, the leaf angles are more like sort of vertical, whereas if you're from a higher latitude, it's vice versa. So there are a lot of variations related to this, but also environmental drivers impact leaf angle variations. This is one of the earlier work from Earth Forces group that shows there's a strong correlation between leaf water potential and the steady state leaf angle. So what you're seeing here, on this side, this is high water, so less water stress, and for plants that are more water stressed, leaf angle is much higher, more vertical. This is for soybean. And other environmental factors that impact leaf angle include this one here. This is carbon dioxide. You actually see that for tomato grow under 2 different environmental conditions. This is warmer and higher CO2 concentration. They show more vertical leaf angle and leaf curling, whereas for tomato plants growing like a 400 ppm right now, the leaf angle is different. Soybean and tomato for both. And so there are a lot of variations in leaf angle, whereas in our models, we summarize this in one of our recent papers. In models, leaf angle parameter or parameters, depending on what model you're using, there's usually a fixed number per plant functional type, and it also doesn't change seasonally. And so there are some difference between what we see in the fields in experiments versus what's in the model, right? And one of the reasons I think, there are many reasons for this difference here, but one of the reasons is the difficulties to measure leaf angle in the field. and that some of you probably already know how to measure leaf angle in the field. But just to summarize, there are three main categories of measuring leaf angle. One is to use inclinometer, right? So just bringing inclinometer to the field and measure the mean leaf angle from the central vein or main vein of the leaf. That approach is obviously, you can see it's difficult if you want to capture leaf angle distribution of canopy with 20, 30,000 leaves. Another approach is to use digital camera, or like using LiDAR, the LI 2200 approach. And there are certain assumptions that you need to make using this approach. For example, for the digital camera, you need to make sure the leaves are in this position. If your leaf look like this, you probably cannot estimate the leaf angle accurately using this approach. Whereas LI 2200s, usually they give you the leaf angle distribution of the entire field of view of the canopy, not individual trees. So when we saw this, we started to ask this question, well, is there an accurate, automated, fast, and efficient methods for complex tall canopy, like a tree canopy, that many AmeriFlux sites are located in? And the answer, well, as you can guess from what Martin has mentioned, is terrestrial laser scanning. This is collected by my student Rong Li. Here, this is a flux tower site near UVA, and you can see that terrestrial laser scanning provides detailed information about the canopy. You can even see points, clouds of individual leaves, and we're gonna see the tower here in a minute. So at the instrument we're using is from Leica, and the resolution, the uncertainty here is at 10-meter distance, it's about 4 millimeter, and the angular, the beam divergence is about 0.5 milliradian. So pretty accurate data set. And you can also sort of look at individual trees that's collected, cut out from point clouds. This is from Sketchfab. If you're interested, I'm happy to send you the link. You can see the details that you can get from this. This is a magnolia tree on UVA campus. All right, so what can we do with this point cloud is that we develop an algorithm called TLS Leaf. Kudos to my former postdoc, Atticus Stovall, who's now currently working at NASA, and also assistant research professor at University of Maryland. So basically taking the terrestrial laser scanning point cloud, graded TLS data, you can estimate the normal of the surfaces. And so here's an example here that when you zoom in and look at the leaves, and you can estimate the leaf angle, not only the mean leaf angle of that leaf, but also the variation of angles of the leaves. And when you take all those data together, going through steps like classify leaves and wood, filtering, and also including some noise filtering, things like that. Eventually, you'll get something like this leaf angle distribution, and also fitted with beta distribution. This all sounds exciting, but I also want to put a note here that there are also caveats of this TLS approach. One thing is it's quite expensive as of yet, right? So like a Leica instrument we're using is costs about $70,000, and also there are some uncertainties for related to occlusion, right? So, but that can be quantified, and Martin actually has a paper about the impact of occlusion and how do you what is the best strategy to do the scan to avoid occlusion, and also there are impact of wind. But that's something that you can potentially avoid. Just pick a calm day to do the scan. And with those data, we actually are able to get some new exciting results, right? So this is to look at the vertical distribution of different species if I have friends from Puerto Rico, you probably recognize the one on the left. That's a Cecropia, an early succession tree that are taking over the landscape after Hurricane Maria. And so they all adopted this a horizontal leaf angle strategy because they only put leaves on the top of canopy, trying to overcompete other species. And on the rest of their black walnut, American beech, white oak, those species are typical temporary forest species here in Virginia. And you can see the top canopy has more vertical leaves and more horizontal leaves on the lower part of canopy. But even at the same height, you see some variations in leaf angle. This is one of the work that my student Andrew Jablonski is working on. Also shows the diverse range of vertical leaf angle distribution from different species, right? So some species like tulip poplar take a more like steep leaf angle strategy from top to bottom, whereas some other species don't do that. We're also curious about the seasonal variation of leaf angle, which is rarely documented, especially for forest, temperate forest, or forest in general. And so this is also Atticus' work, and this is in revision for a journal. And so we basically picked 8 sites in a temperate forest near UVA. And what we're seeing here is that there are actually quite dynamic variation in leaf angle, mean leaf angle, both at the canopy level, which is this thing up here, and for the understory. And you can see the most dramatic change in leaf angle, especially in the early growing season and later in the later growing season. So this green line is canopy, and the blue one is understory. And you can see some dramatic changes, especially vertically if you look at the lower part of the canopy, that the leaves are adjusting their leaf angles, plants are adjusting their leaf angles to potentially harvest more sunlight. So, well, why is that important? And there are some earlier work that shows leaf angle's impact on fluxes, like Dennis actually had a paper in, I believe, in 2002 that shows how it impacted latent sensible heat flux, etc. And we did something similar, but also look at the changes over the vertical gradients, right? So if you change leaf angle from 10 degrees here to 80 degrees, the vertical profile of photosynthesis, the difference between temperature of canopy and air temperature, and also the intrinsic water use efficiency all changes. All change. This is from model from a model called Scope with 90 layers, and you can see with the mean leaf angle gets larger and more vertical for the whole canopy. There is increase in both in photosynthesis at both top of canopy and lower canopy, increasing intrinsic water use efficiency. But as for the canopy temperature, you actually see that the top and bottom canopy tends to converge in terms of the difference between canopy temperature and air temperature. So there's some significant impact due to the change of leaf angle. And for more modeling results, you can take a look at our paper this year in Ecology Letters. A collaborator from Cornell, Yixin Ma and Xiangtao Xu, actually run this in BCI, Barrow, Colorado Island, that shows when you change leaf angle from 30 degrees to 70 degrees, so from 30 degree more horizontal to more vertical, you see an improvement or increase in photosynthesis that's in red here in both a top canopy and lower part of the canopy. But the reason for that increase differs. So the bottom canopy, as we understand it, it's because you have more light that penetrates through the canopy that allow you to have more photosynthesis. But the top of canopy, when they turn the leaves more vertically, it's because of the less water stress. So I have one more slide. I will end the presentation here by saying that I think being able to measure leaf angle at an individual scale at such a detail really not only help us to understand the fluxes better, but also can help us to understand more other ecological questions. One of the things that we're very interested in is what is the role of canopy structure in the sort of plant economic spectrum, right? So we know that leaves with higher nitrogen content, have perhaps a lower leaf mass per area. But what about the canopy structure? And plants are integrated units. Leaves are not standalone on a canopy, so they must co-vary with other traits in some way. And when leaf angle co-vary with other traits, it also affects other things that we measure from remote sensing, like the near infrared reflectance of canopy might change. The temperature of the canopy also might have changed. And it also could be correlated with other structural factors like clumping index, right? Do we have higher clumping when the leaf angle is more horizontal, etc. There are a lot of questions to be answered, and now we have a new tool to help us to answer that. And with that, I would like to end my presentation and happy to take questions.
Wonderful. Thanks. Thanks to both of our speakers for really great presentations. And yeah, we have some time for questions. You could put them in the chat. You could raise your hand and unmute, whatever the preference is. I can start us off. You talked, you went into great detail on the leaf angles, but are you working on connecting that with sort of cross correlating that with other variables? What's your next direction?
Thank you. That's a great question. So I think one thing that potentially, we can even collaborate with whoever interested in, and including Martin, like what is the relationship between, for example, leaf angle and clumping index? How do we separate those even from TLS? And also something that my student is working on is to, try to relate other leaf traits with the leaf angle. And yeah, that would be an interesting thing to explore too. In addition, perhaps this is related to the remote sensing community. How do we estimate leaf angle from using other remote sensing approach? Yeah.
Great, thank you. And there's a question in the chat for Martin. Saying that using TLS often leads to data gaps, and can you explain why that is? And can you remind us what TLS stands for?
Oh, so what TLS stands for is terrestrial laser scanning. And so why does it lead to gaps? That's caused by occlusion. So laser pulses travel through the canopy and they get intercepted. So by leaves or wood. So once they get intercepted, there is a point where no more energy travels forward, and there can be areas like for terrestrial LiDAR is mostly at the top of the canopy, so you can have some holes in there. I think this is frequent in dense canopies, and especially in canopies that have a dense understory, because the laser pulses get intercepted very early as they're going upwards. And the solution to that is, in my end, is increasing the number of places you put your instrument. So you just have a very high density of scans, and it just ends up at some point making its way up.
Just try again. Okay, and then we have Andre writing in the chat to both of you to please talk about validation of the data products and what references you use. Martin, why don't you start?
Sure. So the way, well, the mapping of the leaf area itself is, there's no other reference data to validate that. It's very difficult. We tried once with somebody at the crane and they actually separated space with some ropes, and then they collected leaf area and inside these cubes. And that we didn't end up doing much with that data, but that was an extremely difficult process. They had this bucket lift that went up, and it was very difficult. But once you integrate the leaf area from all these little voxels, you come up with a leaf area index value, and we did compare that against the field, like best estimate. And yeah, that validation works out well, but we can't validate, like, even the vertical profiles are we can compare against other measurements, but they are not necessarily more accurate.
Do you want to add something?
Yeah, I could add something about the leaf angle validation. So we did that in our paper, a couple ways of validating leaf angle estimation from TLS. One way is to, you can create this fake leaves, and you know its angle, and then use TLS to measure at increasing distances and look at how accurate your TLS estimation is compared with the truth. The challenge of that approach is, even fake leaves, they vary a lot, even within a single leaf in terms of leaf angle. So we're actually trying to even add more validation by just using a flat, surface and see how it goes. The other way to validate is to create some virtual forest using existing, point cloud data that its angle, and then you can pretend that you put the LiDAR instrument in the forest with different occlusion conditions, and then see how the TLS performs. So that's how we're doing this. For tall trees, it's definitely, like Martin said, it's challenging because you need to first go there, get to the top of canopy, and then measure leaf angle. But also you need to be able to find the leaves that you measure in the point cloud that you measure. All of those are all challenging thing to do. So yeah.
It's a hard problem. Any other questions for now? We're recording this. You can find it on the AmeriFlux YouTube channel, probably in a couple of days. If not, thank you everyone for joining. Thanks a lot to our two speakers.
Thank you, Kristen.
Yeah, we'll see you.
Kristen.
See you everyone next time.
Yeah, thank you, Joe.
You're welcome.
Bye-bye.
Goodbye.
Thank you both. Have a good weekend, everyone.